Okay, so what we are studying here, electromagnetic induction. Two parts are there. First part is electro, the other part is magnetic. And induction. This word induction, what does it mean? We will also discuss about that. It is basically doing what? It is connecting two things. Electric field, electricity, you can say the two what? Electromagnetic. There are two things. One is the related to electricity and the other one is related to magnetism. Okay, fine. So now let's go and see what does it mean by electromagnetic induction. This is very important for your exam. It can come, okay? Very important, I should say, because this part can come that what explain electromagnetic induction. First, a changing magnetic field intensity movement will induce an electromotive force. This is what we mean by electromagnetic induction. What? Changing magnetic field. If you like have a suppose in a closed electric circuit, a changing magnetic field will produce an electric current. So how does it work? Let me make a very nice diagram to you. Suppose you have a magnet here. So isn't it a magnet? It's a magnet. So suppose you have north pole here and you have south pole here. Okay, so let me change the color and let me make a very nice thing. And from north pole to the south pole, okay, there is, okay, so from north pole to south pole, there is magnetic field lines like this. I told you the other day, didn't I? So the magnetic field lines actually go from where? Like this. They go from north to the south. Can you understand it? What is the direction actually? The yellow is not visible, right? Okay, so what is the direction? The direction is this. So from the north to the south. So basically it goes from north to south like this. So what are they? These lines are? What are these lines, brother? Please tell me. These are magnetic lines, isn't it? Okay, these are magnetic lines, and always their direction are going to be from north to the south. So now is it clear? From north to the south. Okay, so now as you have this magnet, so what is this? This is a magnet. Okay, this is a magnet, and due to the magnet there is magnetic field. And suppose there is a closed electric circuit. Okay, there is a closed electric circuit. What does it mean? Suppose we have a bar here, and around that bar we have like a wire attached wire. So suppose we have wire like this. These are wire. So this bar is wire wound, right? And like it is completing a closed circuit. So suppose there is a connection of battery with this thing. Okay, so this is basically an electric coil. Electric coil. So did you understand it? So now if there is a relative movement between this electric coil and this magnet, there are only two things. One is magnet and the other thing is this electric coil. Okay, so this electric coil is nothing but a closed electric circuit. Closed electric circuit. So now if there is a relative motion, if there is what? A relative motion between this magnet and this closed electric circuit, there will be electric current. So electric current will produce here. So now you understand this? Okay, so we have two things, magnet and closed electric current, and due to the relative motion between them, there will be EMF production, the electromotive force production. What is electromotive force? That has like a different story, right? The electromotive force, it is related to the circuit. To when we are dealing when we're specifically tracking a specific electron, right? And that is entirely like traveling the whole circuit and coming back to its like position from where it started its journey. The work done to do this is called the electromotive force. So somehow it is related like this, right? So yeah, you can see the definition from the book, but that is what we know as electromotive force or EMF. So we have been able to understand what is electromagnetic induction. What you need to write in the exam is a changing magnetic field. That means intensity movement will induce an electromotive force. And now this can be thing that suppose you have a thing like suppose you keep this coil stationary, okay? Stationary. Try to imagine you are keeping this coil stationary, and then what I'm saying, brother, you keep this coil stationary and then you bring this magnet closer to this coil. So there will be the change in the magnetic field, isn't it? Or specifically, I can say change in the magnetic flux. So we are going to also talk about that. So what is the electromagnetic induction? Faraday's law. What is Faraday's law? That is the induced EMF in the circuit is proportional to the rate of change of the magnetic flux through any surface bounded by the circuit. So this is the formula. So the formula I already like told you before. Also, let me write it. The EMF or electromagnetic force, that is equal to negative d phi dt. Okay, d phi b dt. Here phi b, this is the magnetic flux, right? So ddt of phi b, so this is the change of the magnetic flux, right? So do you know the meaning of this thing? This is differentiation, right? So this phi b is being you are doing a differentiation with respect to time. So the change of that magnetic flux is being found, and that is you know, defined as the Faraday's law of electromagnetic induction. So if professor asks you what is Faraday's law, you will simply say this thing. Sorry, you will simply say this thing. This equation you need to keep in your mind, and if you write this in the exam, it is very good. What is that? The induced EMF. This is the induced EMF. Induced EMF. This is the induced EMF in a circuit. In a circuit, it will produce. It will be produced in a circuit. We have already known that is proportional to the rate of change of the magnetic flux. So the rate of change of magnetic flux, it is this thing. This thing is what? The rate of change of magnetic, I can say, with respect to time. The rate of change. Why I am like specifically mentioning with respect to time is because sometimes the rate of change can be with respect to length also. Like when you will study maybe heat transfer or some advanced courses, you will see the rate of change is not always with respect to time. It can be with respect to the length or with respect to the thickness or something else. So I am just telling it, but generally they consider that it is always with respect to time, the rate of change it means. So this thing basically means this. Now you may ask one thing, that why a negative sign is here? Why there is a negative sign? Do you remember why? It is due to Lenz law. Where is my pen? I need to find it. Yeah, it is due to Lenz law. Okay, there is another law that is called Lenz law. Okay, so due to Lenz law, you get this negative sign here. Okay, here in this equation. So now is it clear? Clear to you? If the professor asks you what is electromagnetic induction, you can do it. What is Faraday's law? You can also tell it. But now one thing remains unknown, that what is magnetic flux? What is magnetic flux? Let's talk about this now. Okay, so what was Faraday's experiment? We are talking about that. So I was saying you before, suppose you have a, what is this? NS, what is this? This is magnet. Yeah, this is magnet. Okay, so I am writing it. Okay, this is basically nothing but a magnet. And this is what? Closed electric circuit. Yeah, you can also call it as a coil. Yeah, you can also use a coil here. This is this thing over here forming a loop. Can I call it a coil? Think about it. Okay. Okay. So now see this V. What does this V mean? This is basically nothing but the relative. I talked about this thing before, that there should be a relative motion here. There should be a relative motion. Okay. So here you can see that this V is our relative velocity, you can say. Okay. So relative velocity means here I am keeping this closed circuit stationary. I'm keeping the closed electric circuit stationary, and then I am taking that magnet closer to this electric circuit, and thus I am getting some sort of EMF. I can measure that with an ammeter here. Maybe if you connect an ammeter here, you can see, you can measure that I am getting some EMF. Whenever I am bringing this magnet closer to this electric coil, I am getting that electric current. Maybe the motion can be like this. I'm bringing it closer to this and then I'm again taking it back like this. Or it can also be possible, as I have said, that there should be relative motion between the two things, between the coil and the magnet. So now I am keeping that electric coil stationary. What if I want to keep the magnet stationary? Right? What if I want to keep this thing stationary? This magnet is stationary. Suppose this is the second case. Suppose I am keeping the magnet stationary and then I am having a relative motion by this, that I am actually moving that coil closer to that magnet. This is what Mr. Faraday done. It is his experiment. It is Faraday's experiment. And from this experiment, he got a connection between this closed electric circuit and this magnet. Or specifically, I can say magnetic flux. Or if I say more fundamentally, that is basically a magnet. Because the magnet is always having a north pole and the south pole. And there are like magnetic field lines from the north which are going from north pole to the south pole. So these are like this. So fundamentally that is shown like this. So you can draw this figure and you can go on with this. Okay, take a very close look whether, this is my question to you, you will evaluate whether this thing is correct here or not. Okay, as we already know that in a magnet there are two poles, north pole and the south pole. Okay, this is the thing. And from north pole to the south pole, always we can find those magnetic field lines like this. So there are like some sort of experiments you can also do. We used to do it with magnets, and like if you keep the magnet closer, suppose to a place where there is a sand, there are a lot of sand. Do you mean sand? You know sand we used for the construction processes. There are a lot of sands. If you bring that magnet closer to that, you will see that those things are forming, the magnetic field lines around that magnet. So what is the direction? Is the direction from the north to south or from the south to north? This is your job to find out. Okay. Okay. So now let's go and check. This is Faraday's experiment. We have talked about it. Okay. So Michael Faraday discovered induction in 1831. Oh my God. It was way, way before. It was, sorry, 1831. Can you imagine this time? At this time he did this. He found this. Moving the magnet induces current I. Reversing the direction reverses the current. Yeah, reverses the current. It basically means, suppose you have an ammeter here. Okay, suppose this ammeter, I am just showing it by zooming it. I've just zoomed it. So this ammeter, they have like this kind of arrows that can deflect. So suppose when you are moving the magnet closer in this direction, okay, in this direction. Suppose this is this ammeter is showing moving from this point to this point. Okay, so but when you are reversing the direction of that ammeter, when you are reversing the direction of that ammeter from this side to this side, from according to this direction. At first it was from this to this, and now it is from this direction to this direction. So now you will see that the deflection is also in a reverse way, in a reverse manner. Okay, reversing the direction also reverses the current. Okay, and then moving the loop induces a current. Yeah, if you can also move the loop by keeping the magnet stationary. The induced current is set up by an induced EMF. This is what induced EMF is basically known as. So these are the very important points that you can really mention. Okay, these are the important points you can talk about in the exam paper. The induced current is set up by an induced EMF. So can you write all of these things? Nice. Okay. So now now that we have already talked about it, changing the current in the right hand coil induces a current in the left hand coil. So suppose this is what you can also see. Suppose you change the current. So there are two currents. There are two coils basically. You can see here. Two coils. You can see this is the coil left and the other one is right. Okay. So if you change the current in the right hand coil, suppose you have a source. a current source here. So if you change the current of this right hand coil, it will induce a current in the left hand coil. It will basically inducing it. There is no physical connection between these two coils. Is there any physical connection between these two coils? No, there is no. So that means without any kind of physical connection, how you can change the currents from one coil to the other? Like you are changing the current in the right hand coil and it is inducing current in the left hand coil. Isn't it amazing? This is what you call this induced current does not depend on the size of the current in the right hand coil. No matter how the size of your current in the right hand coil, it doesn't depend on it. It just induced current is only depends on di dt. Okay, di dt. It depends on the rate of the change of the current, di dt. Isn't it? Okay, we are actually studying it very, in a very brief manner. But actually, this is what you need to write. If you write like this, you will get like almost full marks. Okay, these questions are asked in the first semester courses in a very, I should say, a frequent manner. These things can also be asked in your Viva. Okay, now we are going to talk about magnetic flux. Okay, in the easiest case, with a constant magnetic field B. So this is basically, this B is the magnetic field. Do you remember there were magnetic field lines coming from the North Pole and going to the South Pole like this? So yeah, in the easiest case, with a constant magnetic field B and a flat surface of area A. So this is basically flat surface which is having area A. The magnetic flux is nothing but magnetic flux. It is represented with this thing. Okay, phi B. You say this phi. This is the Greek letter. Okay, how you pronounce it? Phi. 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 Okay, actually when you study advanced fluid mechanics, in those cases this phi, it can also be, it also represents the complex it basically potential function. It is basically potential function, but what I just told you now, just forget that. Okay, just forget this thing, because this is a Greek letter and its pronunciation is what? Phi. Okay, now phi is basically nothing but the dot product of B and A, because see, B is also a vector quantity, A is also a vector quantity. Do you know what is vector quantity? It has a magnitude and a direction. A vector quantity needs a magnitude and a direction, and a scalar quantity only requires a magnitude to be represented. That's it. Okay, so this basically, these two things, the area, this is also a vector in this case, and the magnetic field B, this is also vector, and vector can be represented in many ways. Suppose B, this is a vector, this is vector, this is also vector, and this is the value of the vector. Okay, like this you can write it. Okay, so okay, what is the unit of the magnetic flux? That is basically this phi. Okay, magnetic field has unit Tesla. Okay, and area has what? This area has a unit meter square. So what you are getting, this B is having an unit which is called Tesla, and A is having unit that is called meter square. So Tesla into meter square, and if you multiply with this two, we are getting 1 Weber, Weber, Weber. So basically this is the thing that you need to keep in your mind. Okay, so when we talk about magnetic flux, this is basically nothing. What you do? Okay, we are talking about magnetic flux. Okay, so I am not going to see. We are just drawing this thing. Then we are showing the A. We are showing the magnetic this B. Okay, these are vector quantities. I told you. Okay, so this is A and this is B, and this is a flat surface. What is this? Is a flat surface which is having area A. So magnetic flux phi B is basically nothing but B dot A. B dot A. And what is the unit? Unit is Weber. And Weber is equal to Tesla into meter square. Okay, did you get it? Only this thing is what you need to keep in mind. And for the revision, I will also provide you this thing. You can also revise. Okay, nice. And then let's go. This magnetic flux, I told you that when B is not constant, that means the value of the magnetic field, that is not constant. This was in the case when the magnetic field was constant. Can we keep this in our mind? Can I highlight this? Yeah. Constant magnetic field B. it was constant magnetic field B. The value of B was not changing with respect to time. But now, what if it is changing? When B is not constant, when B is not constant, or the surface is not flat, or the surface can also be not flat. Okay, one must do an integral. Break the surface into bits, small dA, lot of dA. The flux through one bit is B dot dA. Okay, and B dot dA, what do you mean by this thing? B dot dA, what do you mean by this thing? Do you know? This is dot product. And what is the dot product? We've already studied. Suppose A dot B. And there are two vector quantities A and B. And if you dot product them, if you find that, if you are trying to find the dot product, it is going to give you AB cos theta. Okay, this A is the value of this vector A, or the magnitude of this vector A. Okay, so this is called dot product, dot multiplication or dot operation on two vectors. So AB cos theta. So see here, what we have? We have, I'm changing the color. We have B in dA, B dot dA. We have just, we have just broken the surface into a lot of small surfaces that are called small dA. As the area is also changing. So B dot dA. Okay, B dot dA. So if we are finding a lot of small a, that is called dA, B dot dA, what will be here? In place of a, you can imagine B. In place of B vector, you can imagine dA. So these are going to be B into dA into cos theta. What is theta? Theta is the angle between these two vectors. It's not basically nothing but the angle between these two vectors. You can imagine here the surface area. Suppose if you look at this place, if you look at this surface, the value of it is constantly changing. Here it is getting little smaller. Here it is getting some other value. Here it has got some other value, and ultimately it has got some other value. So we are taking an elementary area. This can be called as elementary. Elementary area, that is dA. Okay, see dA, the value of this is basically dA. If we integrate a lot of dA, we are going to get A over some, we need to put some, lower limit and upper limit. If we do that, we are going to be getting the area. Did you get something, brother? Did you get something, or it just bothered you? Be honest. It bothered you? Okay, so even if you don't get a lot of things, no worries, you will get, eventually you will get it. Okay, no worries. So here B is not constant. See, the value of the B is also changing, and its direction is also like changing all the time. And at a certain point, we are taking the value of B by taking a tangent, that is B, and the area dA. And here the area, sometimes, so area, it can also be vector, and its direction is something like this, from here to like this. Okay, so you can keep this in mind, and further we will decide why, we will also discuss why it happens, and we will go deep into that. But for now, you can keep this in mind. And this flux through one bit is this thing. So we have just provided the value B dA cos theta. See, B dot dA, there were two vectors, B and dA, they are two vectors. Now you just put the value of B and dA and cos theta, so you get this equation. Okay, dot product of two vectors giving you this thing. So end of the day, you are getting B dA cos theta. So this is the value. So add the bits. Okay, so now as we have already talked about the magnetic flux. Okay, we have learned magnetic flux in two cases. One case where constant magnetic field B, and flat surface of area A. We simply just do what? We just do B dot A. Okay, phi B. And if they are not constant, then we do what? Phi B is equal to B into dA into cos theta, where this theta is the angle between the two vectors B and dA. So did you get a revision of this thing? Yeah, I have just told you. This is what magnetic flux is. In the equation, we had this term magnetic flux, so we have to learn it. Faraday's law. Moving the magnetic flux, see, now we are going to be dealing with more like perfection. If look at this image number 1, sorry, look at this image number 1. Okay, we have, what is here? What do we have here? Please tell me, brother. What do we have here? It's a coil. Okay, and what is it? It's a magnet. So moving the magnet changes the flux. Okay, second, in the second image, changing the current changes the flux. We already talked about it. And Faraday, he says that changing the flux induces an EMF, and that EMF, the induced EMF induced around that loop, is basically nothing but minus d phi b dt equals the rate of change of the flux through that loop. So this is Faraday's law. So this is the equation. This is the equation you need to keep in mind, and all the story behind it you need to keep in mind. And what is this induced EMF? Okay, I talked about it. What is like electromagnetic induction? I talked about it. I talked about what is actually phi b, what is the magnetic flux. There in two cases, in constant the magnetic field, flat surface, and where the area and the magnetic flux is constantly changing. We have talked about the both cases, and that change with respect to time. And this negative sign is basically due to Lenz law. I have also talked about that. Due to Lenz law. Okay, due to. Okay, so we are going to what is Lenz law. As we already talked about Lenz law, now we need to know a little about Lenz law. I will give you an overview, you will understand it. Faraday's law gives the direction of the induced EMF, and therefore the direction of any induced current. We are going to take a look at this, any induced current. Lenz law is a simple way to get the directions straight with less effort. What is Lenz law? It is the induced EMF is directed so that any induced current flow will oppose. The induced current will oppose the change in the magnetic flux, which is basically causing the induced EMF. It means when you are bringing that magnet closer to that coil, that magnet is inducing some EMF into that coil, isn't it? Or into that closed electric circuit. Is it? Is it true? Okay, so why it was induced? Because of the relative motion of that magnet. So that induced current is trying to oppose the reason why it was induced. And the reason was that it was kept stationary, that electric coil was kept stationary, and there was relative movement or relative velocity of magnetic field with respect to that electric coil. It is something like that. Suppose you were born here, and after being born, you are trying to kill your father, the reason of your birth. So this is what it will oppose the change in the magnetic flux, which causes the induced EMF. Like this is just a simple example by which you can keep this in mind. So you understood the Lenz law. Okay, this is easier to use than to say decreasing the magnetic flux. It means EMF creates additional magnetic field, and increasing the flux, EMF creates opposed magnetic field. Okay, so if you just ignore this, if you understand this, it's okay, and if you are ignoring this, it's okay, no problem. Lenz law is this what you know. So that's it. You have been able to know what is Lenz law. See, this B. This B. Take a look at this B. Because of the motion of this V in this direction, there is like the Lenz law, which is trying to oppose the reason why it is being induced in this specific coil. Okay. If we move the magnet towards the loop, the flux B will increase. Lenz law, the current induced in the loop will generate a field B opposed to B. So see, now due to the magnetic field line, due to those magnetic field lines, you are getting some induced currents in this circuit. See, this moves in different directions. If you move the magnetic coil in this direction, suppose from it is in this direction. If you reverse the direction of the magnetic coil, it will be in the reverse direction, in the reverse direction.